Welcome to Chapter 2. Today, we focus on encoding schemes and number systems, diving deep into how a computer handles human inputs. Have you ever wondered what exactly happens when you press A on your keyboard? The computer intercepts that physical action and translates it via internal mapping to a predefined code. This process is called encoding. It's the mandatory mechanism of converting human data into an equivalent cipher so that multiple distinct hardware brands function seamlessly. Historically, we standardized this using ASCII. Standing for American Standard Code for Information Interchange, it was developed in the early 1960s to completely unify digital communications. ASCII originally dedicated exactly 7 bits of memory per character. This mathematically allows for 128 unique combinations, which beautifully maps all English letters and standard punctuation. But what about global computing? ASCII famously lacked the memory addresses to support massive international character sets, severely limiting non-English developers. In response, India developed ISCII in the 1980s. Leveraging an expanded 8-bit architecture, this Indian script format allowed 256 unique regional script characters to process accurately. ISCII cleverly retains the original 128 ASCII codes at the bottom for normal English functionality, while reserving the upper half strictly for linguistic regional symbols known as aksharas. Today, we just use UNICODE. This incredible global standard replaces all older fragmentation by assigning a unique numerical string to literally every written character on the entire planet. UNICODE is fully compatible backwards with ASCII and deployed universally in modern web formats like UTF-8, UTF-16, and UTF-32 depending on memory requirements. Now that we've encoded letters into code arrays, how do hardware systems interpret those numbers mathematically? Let us introduce strict number systems. Computing utilizes positional number systems. This means a symbol's numeric value is governed totally by its physical position in the chain, multiplying exponentially the further left it sits. As humans, we naturally count using the decimal number system, or base 10. Leveraging precisely 10 numerical digits, it scales natively by multiplying powers of 10. Computers do not. Processors operate using exclusively binary, or base 2. By reducing variables to just ones and zeros, physical logic gates can calculate using high and low electrical voltages. This hardware limitation dictates software completely. The CPU cannot interpret 10 separate states seamlessly, so mapping logic states as pure binary is the safest approach to robust hardware architecture. Unfortunately, staring at screens filled exclusively with millions of binary zeros and ones causes intense human error. Thus, engineers frequently compress this data into octal systems, or base 8. Octal natively limits values between 0 and 7. Mathematically, any 3 binary data bit subsets compress with absolute perfection into a single, clean octal digit. However, modern 64-bit processing relies almost entirely on the hexadecimal number system. This is base 16, adding alphabet letters A through F beside our normal numerical digits. Hex is incredibly powerful. Because 16 is 2 to the power of 4, every sequence of 4 individual binary bits compresses seamlessly into one highly efficient hex alphanumeric symbol. You see hex all the time, from allocating explicit hexadecimal memory addresses in computer RAM to encoding 6-digit RGB color matrices commonly used in web design. Due to overlapping architectures, computer science requires fast base conversion techniques, methods to effortlessly translate massive integer chunks quickly correctly between these variable bases. If you want to map base 10 into binary, you repeatedly perform successive division by 2, tracking every remainder bit and stacking them perfectly in reverse chronological order. Conversely, to unwrap binary data back into human decimal, you use positional multiplication. You literally multiply every 1 or 0 by its corresponding exponential positional value over the grid. When dealing with fractional components behind decimal dots, engineers carefully manipulate these conversion algorithms using successive multiplication frameworks instead of strict division. That wraps up Chapter 2. Encodings perfectly standardize alphabets, and positional number systems construct mathematical data states using native binary architecture frameworks. Thank you.